In this example, we're asked to try to diagonalize this given matrix. So the way to begin this process, just always to diagonalize a matrix, is to first find its eigenvalues. And we do that using the characteristic polynomial, which comes from the determinant of the matrix A minus lambda I. So in this case, the A minus lambda I matrix would look like this. So we have A here to negative 2 6, okay, minus lambda times the 2 by 2 identity matrix here. And so that's equal to this matrix A minus a diagonal matrix where the diagonal entries are just the lambdas. And so this A minus lambda I matrix looks like this. So we have 2 minus lambda, and then we have 6 minus lambda along the diagonal, and then the other two entries remain the same, so 2 and negative 2 here. Now the characteristic polynomial is the expression for the determinant of this matrix. So we want the determinant of this 2 minus lambda, and I should give myself a little more room here. Let's see, negative 2, 2, and 6 minus lambda. Okay, so since it's just a 2 by 2, we can do that sort of cross-multiplying thing to find the determinant. So we start with the 2 minus lambda times 6 minus lambda. Minus the negative 2 times 2. Okay, so multiplying this out, we have 12, let's see, and then minus 2 lambda, and then minus 6 lambda, so that's minus 8 lambda. And then we've got negative lambda times negative lambda, so that's positive lambda squared. And then minus negative 4 back here, so plus 4. And so if we rearrange that a bit, it's just nice to have the squared term in the front. Minus 8 lambda, and then the 12 plus 4, so that's 16 here. And so that factors as lambda minus 4 times lambda minus 4. You're looking for two numbers whose product is 16, the sum is negative 8. So this is equal to lambda minus 4 squared. And so, like I said, this right here is the characteristic polynomial. Characteristic polynomial for this matrix A. The eigenvalues are the zeros of the characteristic polynomial. So this matrix only has the one eigenvalue 4 with algebraic multiplicity 2. Remember that the algebraic multiplicity is the multiplicity of the 0, in this case 4, as a 0 of the polynomial. So, okay, the only eigenvalue is 4. That's really all I need to know to move forward. But I mentioned the multiplicity just as a review. Okay. So once you find the eigenvalues for the matrix, then you should find a basis for the corresponding eigenspace or spaces if you had more than one eigenvalue. So basically, we want linearly independent eigenvectors for each eigenvalue. Okay, so if we're going to work with the lambda equals 4. And so the corresponding eigenspace is denoted E4. So that's just a basis for the collection of all eigenvectors corresponding to lambda equals 4. Now to find that, we're looking for solutions to the equation AX equals lambda, which in this case is 4 times X. Because remember, x is an eigenvector if a times x equals some scalar multiple of that vector. And in this case, the scalar multiple we already know needs to be 4. Okay, so the matrix A is that 2, 2, negative 2, 6 matrix that we were given, times some vector x. So we're trying to learn about this vector x. So I'm going to call the entries x1, x2 for now. These unknown entries of the vector x equals 4 times the vector x. So I'll use that same notation here, x1, x2. Now if I multiply this out on the left, I have 2 times x1, 2 times x1 plus 2 times x2 for my first entry. And then second row, I'll have negative 2 times x1 plus 6 times x2 equals, so 4 times that vector, so we just multiply each entry by the scalar 4. And from there we can set up a system of equations. Here it's setting the first components equal to each other, and then setting the second components equal to each other, so negative 2x1 plus 6x2 equals 4x2. And then we should combine like terms. So in that first equation, I would subtract 4x1 from both sides. So I'm going to subtract 4x1 over here. And that gives me, let's see, negative 2x1, positive 2x2 equals 0. And then I want to do the same thing in the second equation, except here I'm subtracting 4x2 and combining it with the 6x2 over here. And so the resulting equation there is actually exactly the same. Negative 2x1 plus 2x2 equals 0. So the augmented matrix corresponding to this system looks like this. If I want to reduce this matrix, since the rows are already equal to each other, I would probably first eliminate the second row by taking negative 1 times row 1 and adding that to row 2. So that's, I'm adding positive 2, so I get 0 here. I'm adding negative 2 to 2, so that gives me 0, so I get this row of zeros. Next, I'd like to have my pivot, so my leading non-zero term to be 1, so I'm going to multiply row 1 by negative 1/2. And that negative 1/2 times the negative 2, so that's positive 1. But the second entry will be negative 1, and then 0 times negative 1/2, so that's still 0. Okay, so I have the augmented matrix in reduced form. So I now take this first row and write the corresponding equation here. So that's x1 minus x2 equals 0. So x1 equals x2. So in any vector that's an eigenvector corresponding to lambda equals 4 is going to have x1 equal to x2. So our vector x is going to look like this. I mean, we wrote x1, x2, but it turns out that x1 needs to equal x2. So this is really more like x2, x2. The entries are going to have to be equal. And so we could describe all vectors of that form by expressing this as x2 times 1, 1. So any scalar times the vector 1, 1 would give us an eigenvector corresponding to lambda equals 4. So this right here I would probably use as my basis for E4. Now, since that's the only that's the only basis vector we came up with for the eigenvectors for lambda equals 4. This matrix is not diagonalizable. We started with a 2 by 2 matrix. We found only one eigenvector here. So when you form your diagonal matrix, or when we diagonalize this thing, we're trying to write it as A equals P times a diagonal matrix D times P inverse. The matrix P here is made up of the eigenvectors. And so I bring all that up just to say this would need to be a 2 by 2 matrix, which is why we need two eigenvectors to go along with this given matrix A. And since we only found one, like I said, this matrix A is not diagonalizable.